So I was explaining before I started the recording that I will give us like a talk of about 40 minutes to 1 hour, and this is there are other people that are also invited to participate in the course. But after that, I will explain how will be the course, how will be the tests, and so on, the classes and the project and so on. Okay, so first of all, I will give this talk about model-based closed-loop reservoir development and management. It's very important for us to understand this because the courses will be very focused on this subject. How we use reservoir simulations to in a day-to-day life of petroleum industry, how we use reservoir simulations to forecast production, how we use uh, reservoir simulation to take decisions and so on. Okay. Please let me know if you are having any problem in seeing the slides as well, okay? So first of all, reservoir simulation is a discipline that is very integrated with other disciplines. So I'll start saying this is very important for you to understand at least these three areas here that we are talking about. Of course, reservoir engineering is the main uh, discipline we have to put into the simulators, but also we have to understand about the geoscience because we need to build the models, and these models have to be as reliable as possible to represent the real reservoir for us in order to take the decisions, okay? Also, it's very important for us to understand about, can you see the pointer here? Right. Seeing about the production engineering. We are going to have a talk about this, but of course, we're going to produce the petroleum, the gas, and the oil that's in the reservoir. And in order to produce, we have to go into the well and into the production systems. And because of that, the petroleum facilities, the facilities and the surface facilities are the boundary conditions for the reservoir. And as you're gonna see in the course, if the boundary conditions are wrong, then it doesn't matter if our representation of the reservoir is very good, if our model has a billion cells and this one, if the reservoir, the boundary conditions are wrong, we are forecasting wrong production, okay? And also, many companies don't have this economic evaluation integrated with reservoir simulation, but for us, it's very important because all the decisions we are going to take using reservoir simulations will involve any kind of economic calculation. For example, if you want to inject a polymer in a reservoir, we have to know how much the polymer costs, how much will we improve production if we inject the polymers and so on. If you're going to inject water, if you're going to drill 10 wells or 20 wells or 5 injectors or 8 injectors, all these decisions at the end, in order to take a good decision, we have to do economic calculations. And I think this is very important to be integrated with the simulation, okay? So in order to do this, we are going to use this concept throughout the course, which is closed loop field development and management that I'm showing here. We are calling it model based because we are going to base our decisions in the simulation models. And we also we are not doing in the course, but in today, petroleum companies and also in Unisyn, which is our reservoir simulation group, we are trying to also use data to improve these decisions. But in the course, we are going to concentrate in the model-based decisions, okay? Which is the decisions we are going to take based on this reservoir simulations that we are using. So in order to do that, several companies and several universities use this concept of closed loop decisions. I'm going to explain this in detail, and you are going to see a lot of this in the course, in the other seminars you're going to have. we after this talk, I will explain how the talks and the classes are organized. They are organized more or less in this order that I will explain this closed loop concept here. So imagine that this is the reservoir. We have the reservoir here, and we have to our main function is to uh, objective is to forecast production, which is this, and to select the best way to produce from this reservoir. So we are focused on producing the most we can, maximizing normally our objective function, which is, for example, the net present value of the field or the oil production and so on. So we want to integrate, select this production strategy and then produce as most as we can and have a forecast of this production as as much precise as we can. Okay. In order to do that, we need to construct reservoir simulation models. Okay. The reservoir simulation models are constructed in this here in this green part here. So what's important in this green part? We have to take as much information as we have from geology, from seismic, from well logs, from well tests, from fluid properties, laboratories, and so on. We're going to take as much data as we can here to construct what we call these high fidelity models. Okay, high fidelity models are the models that we can build in the today's computer that are as good as possible to represent the reservoir, the fluid, the rock, and so on. Okay, but of course, if you build these models as accurate as possible, these models can take days to run, and even in the clusters we have today. So in order to have reasonable times for reservoir simulation and reservoir simulation that can be useful in the day-to-day life from the company, we transfer this data to what we are calling today the fit-for-purpose simulation models. Okay, that we call, we're gonna see in the course, we call this in our group the medium fidelity models. Okay, the medium fidelity models is the models that are as they are not as accurate as possible, but they are good to take the decisions to select the production strategy and to forecast production. So instead of running in days, they can run in hours or even less than an hour, and the decisions still can be good using these models. Throughout the course, we are going to explain why we are not using these high fidelity models. Not only because these are faster, because these are models, and they, of course, they are different from the real reservoir, and sometimes these models they are as good as these models to take the decisions we can take for this objective that we are inputting here. For example, if we want to forecast production, we have to build models that are as good as possible to forecast production. Even if the models are not so high fidelity models here, we can forecast production with accuracy using these fit-for-purpose models here. And as we have an error from these models, of course, sometimes the errors are so big in this model as in this model. So we are going to talk a lot about these errors here, and some of the classes we can explain how these models are built and how they are using, how we are gonna use these models for the other quality. Okay, so if you are not very familiar with reservoir simulation, don't bother to understand this right now. We're gonna talk a lot about this in the other classes. Okay, but feel free to interrupt if you have questions. Okay, when we have these models, we are gonna use them to do these two main activities here, which is forecast production and to select production strategy. So we need to check the models are okay. If they are okay, I'm gonna explain what the models can be okay if they honor all the data we have, not only static data that we use to construct the model, but also to the dynamic data. We are going to explain this in this part here. So once we have the well tests, once we have the production, once we have seismic 4D, for example, the models have to be good enough to reproduce this data, this past data, which we represent here in the red color, what we call data simulation. The data simulation is the name we use for what maybe some of you know by history matching. And we are going to explain a little bit also why we are not calling history matching anymore. Of course, history matching is very well-known activity in petroleum companies. It's very important for you to understand that data simulation and history matching are almost the same thing. But we are calling data simulation in order to explain that our main focus is not to match data. Our main focus is to have good models to these two main functions here, which is forecast production and to take decisions. So in order to do that, we differentiate a little bit in our group, data simulation from history matching. But feel free to call history matching if you prefer. We're gonna refer as both in the course, but we are going to explain this is a small difference between them in one of the classes, okay? But once we have models that can honor the past and have a good reasonable time to run, we go into this blue part here, which is what we call life cycle production optimization. Why we call life cycle production optimization, which ended recently, was long term, but this is the production strategy we are going to implement in the field from tomorrow until the last day of the production of the reservoir. That's why it's a very complex task, okay? But we need to do that in order to forecast production. So we need to know how will be the platform, how many wells, how many producers, how many injectors, how much we're going to inject, what is the boundary conditions from the producers, from the injectors, how we're going to inject polymers or water or so on. So in order to forecast this production from and know how much the reservoir will produce, we need to do this process here, which is very complex. We're going to talk about this in several classes, but this is the blue part that we call the life cycle production optimization, okay? Once we decide here the best way we can produce the reservoir, we implement this decision into the reservoir. It can be drilling a new well, it can be drilling a new injector, it can be close a well, it can be close a valve, or so on. And this production strategy we're going to talk about is very complex, but we have to implement this in the field in order to produce, okay? And of course, we have what we call here operational noise, which is some things that happen that are not planned. For example, I can plan to close a valve, but when I'm going to close the valve, the equipment is broken and I cannot close. So the production strategy, that ideal production strategy that I optimize in this part, not always can be implemented in the reservoir. That's why we have this operational noise here. We have delays, we have equipment that can break, we have some tests, maintenance, and so on. So all these things here can happen. So it's important to include them here. We are going to talk about how we're going to include this in this model, but it's important to include because if we don't have this, we're going to have a bias in the solution, okay? Which is a bias. If we understand that the equipment will never break, will never be delayed, and will be no problem from here to 20 years ahead, then we are going to have an optimistic production strategy, which is not good. Okay, we are going to think that we are going to produce more than we produce. Sometimes can be less. Some things can happen to improve, but normally the problems will be from the side of decreased production. The problems will close wells, close valves, or platform, and so on. So that's why I normally say that we have a bias here, because this operational noise has a bias. It's not only it's much more for the pessimistic side than from the optimistic side, okay? But once we have this, we implement this production strategy in the field, And once we implement this, we're going to measure the production, measure, for example, the fluid movement by a seismic 4D, and so on. We're going to measure this data. We also have a noise here in the data. And once we measure this data, we go to the next cycle. And what's the next cycle? We're going to see if the models are okay. If they are okay, I will see if the production strategy remains the same. And if it remains the same, I keep doing the next cycle and so on. If the models are not okay anymore, we're going to see this also in a class, in the course. Then I have to change the models. I can change the high fidelity models, what we call a big loop here, which is changing the geologic concepts of the reservoir, changing the images, the permeability, porosity, and so on. And then we transfer the data again to these medium fidelity models or feature purpose models, and so on. We go to the next cycle. And sometimes we go, the differences are not so big. We can go directly and change the models here. We don't need to go to all this process. So we have these both options here. To change the simulation models or to change the high fidelity models that will be changed to the simulation models, okay? And we keep doing this cycle every month or every 6 months, and we check that the models are okay, change the decision, and so on, and keep doing this cycle again and again and again. And why it's very important for you that are taking the class of reservoir simulation to understand. Many of the places, or many of the reservoir engineers as well, work only with data simulation or history matching, or some other just work with production optimization or construct the models. Sometimes people don't realize that these three activities are very integrated, and in order for you to be a very good reservoir engineering and reservoir simulation person, you have to understand of these three parts here. It's not possible for you to be a good user of a simulator if you don't understand how good is your model, what is the limitations of your models, how much you're gonna trust in these models for the future, and so on. If the models are not okay, you have to know how to improve them, which we do here in the red part. And if they are okay, if they honor the pass, we're gonna see how we're gonna use this to select the best way to production the strategy. It's not possible to understand only of one of these areas, okay? And of course, this is a multidisciplinary. You're gonna see about the classes that here we have geology, geophysics, we have to understand about optimization, statistics, reservoir engineering, production engineering, economics, and so on. So of course, you cannot be understand about everything very good. Of course, we're gonna have a major, but of major concern, which can be one of the scholars. But it's very important for you to understand how to interact with the other colleagues, okay? So we are gonna talk a lot about these three things here throughout the courses. We're gonna start talking about the green part, about how to build the models, then how to assimilate the data, and how to use the models to take decisions for production. And we are going to talk not too much about this black part here in the top, which is for us is very recent, is more research than a real activity. But what we are observing today is that reservoir simulation is very well used in the industry, but they are used more for life cycle decisions than for short-term decisions. What I mean by short-term decisions. For example, people use the simulation to know how many wells we're gonna have, what's the best cycle for WAG, for example, or something, or to decide if it's good or not to inject polymers and so on. But they don't really use reservoir simulation to decide the next day or next month's productions or changes and so on. And it's a challenge for us in our group. That was a challenge from the industry, and to try to use reservoir simulation models not only for this blue part here, but also for this black part here in the top, which is the day-to-day life of the reservoir. So we are not talking too much about this in the course because this is not a traditional activity of our group. Probably many companies don't use reservoir simulation for this, but maybe in the future we can talk as much of the blue part, as much of the black part from and the blue part here, because they are complementary. Okay, this one is important to set the main rules, but this one is very important to change the day-to-day decisions that we are going to take. Some people use data to use this, is what we call data-driven and not model-based. That's why we are putting here data-driven support. Okay, of course, if you implement a strategy here and from 10 wells, 3 are not working, have to be closed, we have to do something. Okay, and this something in short term, which is what we call short term. Until we have time to perform another loop here and to change the decisions, we have to take some decisions for the next day, next week, and so on. So this black part here is important. Normally today, the companies, they use data to decide that, but we are trying to see if we can use at least an hybrid model using model and data. Okay. Okay, this is the main topic of our course. We're going to talk about this several times in the course. And if you have any questions, please interrupt me and let me know. Okay. Well, this is closed loop concept here is used in various several industries in several universities, and each one has a particular way to implement this. In our group, we have an implementation of this in 12 steps. Okay, and we are going to follow more or less in the course the order of these steps here. Okay. Unless because of one of our other problems, we change a little bit the order, but we're going to follow these steps, where the colors are the same that we show in the previous slides. First, we have the two green parts here, which is a reservoir characterization in order to build the models, and the model construction. And here in the model construction, we insert not only the models, as we're going to see, that I forget to talk about that in the previous slide. Here you can see multiple boxes, right? Why we have multiple boxes here? Because we normally work in probabilistic approach. In the past, we used to have only one model here, but nowadays we have hundreds or even thousands of models, because as we have many uncertainties from these properties and many uncertainties from the models and so on, instead of relying on only one model, we normally do, I would say hundreds is the most common, 100, 200 models, in order to see not only the reservoir response, but also what is the difference if the property that I was measuring here is not really that precise, or is not that well, or if the image that comes from the geostatistic is not very reliable, and so on. So we have many uncertainties here in the process, and these uncertainties can be not only from the models, from the properties, but also from the models, because the models are medium fidelity models here. They are not so precise. But we also have uncertainties from operational noise. We have uncertainties from economic, the oil price, and these things. So in order to select the best production strategy here, we need to understand about these uncertainties as much as we understand about the models. Okay. So that's why we are implementing this in 12 steps. So here we try to do the reservoir characterization, and then we have the model construction here plus uncertainties. Okay. Once we have these uncertainties here, we go into this red part, which is the part that I explained in the last slide, which is model calibration as scenario reduction. We're going to have here hundreds of 100, 200 scenarios. Then we're going to use these scenarios and use the data in order to see how many of these scenarios can honor the pass and how many are not. So we're going to do some changes in these scenarios and these models in order to, at the end, have at least models that can honor all the data from the past. Once we have the models that honor all the data from the past, we go into this blue part here, which is the life cycle optimization. And we can do this in just one step and just go there in the simulator and optimize production and so on. But normally, this is a very complex problem. We're going to talk about this in the course. So our suggestion is to do this in several steps and very carefully, right? Instead of just putting all the data into simulator and running optimization problem and getting a result, we normally recommend to first to select a base case, understand the behavior of this base case, perform what we call risk analysis. We're going to talk about this. Risk analysis is a statistical technique that we are running all the models we have here and see the response of the model in all these possible scenarios. Once we have this risk analysis, many companies stop their analysis here, saying that we have a risk analysis. But once we have this risk analysis, we have models that are optimistic, pessimistic, models that are more or less. So once we have this, we can improve a lot our production strategy, observing what's happening with these scenarios. Okay, that's our main intention to show this in the course for you. As we have hundreds of models, and it's very hard to work on hundreds and thousands of models, we normally, in order to improve production here, we select some models that represent our uncertainties the best way we can. And we can have as much representative models as our time requires. For example, if I have a week to do a study, I use less representative models. If I have 6 months to do, I can use more representative models and so on. So normally, we are going to reduce from hundreds here to maybe 10, 20 models here, or a little bit more than that, or less than that, depending on the time I have to do this study. Okay. Once we do these representative models, we normally recommend to select the best production strategy for each of these representative models. We call this nominal optimization. It's nominal because we are optimizing each of the scenarios that are representing our uncertainties in the problem. Okay. Don't bother if you don't understand everything I'm saying today, because we are going to have classes about each of these topics here, just giving a general representation of what we are going to see in the course and what are the main activities related to reservoir simulation that I think it's important for you to see. Okay. So once we have this, we go into the production certainty under uncertainties, production strategy. So this strategy that was our base strategy can change according to what's happening to these representative models. We can use several concepts here that we are going to explain in one of the classes. We can use more flexibility. We can decide that our risk is too high, and we decide to go back and acquire more data in order to take my decision. So there are several possible alternatives that comes from this step 10 here. And normally this step 10, we can perform this automatic. That's why we separate this step 10 from the 11. Even when we go into this, what we have today, several tools that can optimize production under uncertainties, that's what we are going to see in the course. We have some improvements that we can make, and we also have to check if the production strategy that I implement it's compatible with the production strategy, with the surface facilities, with the platform that I have, and so on. If they are not, then I have to go back and start this process again. Of course, I already have a main production strategy here. The next step will not be so computational demanding, and so I can go and after a few iterations, I can select the best strategy for the field. Okay. This is a very time-consuming task. Many of you are working with reservoir simulation. You know that you have to perform a lot of thousands and thousands of simulations in order to get a very good solution here. But of course, this time will depend on the time you have to solve your problems. Okay. But at the end, you have to take a decision, and this decision can be to drill a new well, to close a well, to close a valve, to increase production or to decrease production or increase injection, and so on. and we are going to talk about these decisions in the next classes, okay? And of course, here I have a final risk curve and the decision process. And here we have also the short term that I didn't include here because we are not talking about this in the course, but we can, even after having a very good decision from the blue part, for several reasons, I can change the strategy in the short term because of operational problems, because of unmapped uncertainties, and so on, okay? So we are gonna talk about the closed loop, and we're gonna talk about these steps in the classes that we're gonna see until the first test. I'm going to explain about the course after I finish this talk here, okay? Like here, I think I talked about, I separated this, I forgot I had separated these in steps. For first, I was talking about the green part and the red part here, but I think I said that thing about this. We have here to have consistency in the numerical models, we have quality, the range of errors. We have to include uncertainties, which is important. In the red part, we're going to have to use this scenario generation. There is several statistical techniques to do that. We are using in our course a statistical technique that we have developed in our group, that we combine just statistics with light and Ippercume methods, but we are going to see about that as well. And once we have this uncertain production history matching or data simulation, trying to reduce the uncertainties and pass here only the scenarios that honors the past. Okay, so this is the main part. And the past is not only the dynamic data from the well, but also the dynamic data from seismic 4D, for example. So for the examples, we have several examples in Brazil that we have pre-salt and offshore fields. We have seismic 4D, so we have to honor not only the well data, but also this information that comes from this seismic 4D, okay? No questions so far? If you have any comments as well, you can make it, okay? Okay, in the blue part, I had talked about this already. So the main objective is to have this, what we call robust optimization, which is the best decision we can take under uncertainties. We divide this production strategy in 3 categories. We're gonna talk a lot about that as well. We have many things we can change from production strategy, but we divide this in 3 main categories. The first one that we call design variables, which are the variables that we normally select to develop a field. For example, the size of the platform, the number of wells, the position of wells, if you're going to have valves, intelligent valves or not. So all these decisions that we have to take before we develop the field, we call this design or project variables, okay? And of course, these type of variables are very important for green fields, fields that are in the phase of appraisal or development, and they are not so important for fields that already have a production strategy and so on. These other fields, the brown fields and fields that already have a production strategy implemented, the most important variables are what we call control variables that are related to the management of the field. For example, how much water we're going to inject, what's the cycle of the WAG injection, for example, when we're going to close the valves to decrease the water production or gas production and so on. These are the variables that we use to control production in the management phase, okay? And also we have a third category here that we call revitalization variables that we normally have in infill wells. We have some change in completions and so on. And so they are also related to the management of the field, but different from these control variables, that these control variables we can change almost every day, and normally they have a no cost or a very low cost because we can change these control variables very often, and it's not very expensive to do that. But the revitalization variables are different because they require additional investment. For example, you're going to have an infill, if you're gonna change from producer to injector, if you're gonna recomplete a well and these things, they require to stop production, they require additional investment and so on. So the decisions are a little bit more complex than these ones. So we call this group 1, we call this group 2 and group 3. And at the end, we have to optimize the 3 groups of variables in order to have a good production strategy. Okay. Once we optimize these variables, we go into the integration of production facilities, because we're going to check if the variables we select are compatible with the first surface facilities. Of course, we can do these 2 parts integrated. João, we're going to talk about this in one of the classes. We can already optimize this group 1, 2, and 3 variables in a model that is integrated with production facilities, or we can first do the reservoir parts, do the best we can in the reservoir, and then check the production facilities at the end. So we have both options. We're going to talk about these options also in the classes. Okay. And there are several other concepts here that we can use, and Susanna probably will talk about this in the course. That is it useful to have more information? Is it useful to have more flexibility? What's a robust decision, and so on? We're going to talk a little bit about this because we have uncertainties, and as we have uncertainties and we have a risk analysis, we can produce the well in several ways, and these ways can be different from company from company. Some companies are more accept more risks, and they can have a production strategy that are more risky. But if the results are okay, they will produce much more. And other companies, sometimes they have to be more careful because they are faced that they cannot be risky, or it's a small company, it's operating just one field. So in this way, if the risk is too high, they want to, you can take a lot of decisions to decrease this risk. Of course, decreasing risk, we are going to have other consequences and so on. So we are going to talk in one class specifically about that. So there is nothing in the chat. Okay, I was just looking at the chat. Okay, if there is, so at the end, we're going to take these long-term decisions, which is life cycle decisions, now in short-term decisions, where we use models here, and here models and data. Okay, and if we have time, we're going to talk a little bit about this in the course, but otherwise we're going to concentrate in these 12 steps for the life cycle, which is the main activity you're going to face in oil industry if you're going to use reservoir simulation. Okay. Well, we have still a few minutes, so let me see. Now I have a few slides. I put this in this order. Much of these things I already talked about, but I put this in order for you guys that now we will put in Moodle for you, so you can have this material, and you can have a little bit more complete material than I mentioned. But I think I talked about all this. Here we have, in step 1, we are doing the model, the geologic model, the upscaling, the validation of this model. We're going to have the uncertainty modeling and other uncertainties all included in the process. We're going to use as much data as we can from this. Sometimes we use sort of functions. Manuel we'll talk about this step, and I think in next classes, how we're going to use geostatistics to provide the best representation of the properties here, include all the uncertainties. So it's very important to include as much information and uncertainties as we can. Once we have this, we are going to have this model calibration. Sorry, some of the things here are in Portuguese, but I'll try to change. Here's just an example where Manuel did in one of his works. He was doing a model for a fracture reservoir, for example. He constructed the matrix system, the fracture system, they put all together in dual permeability model, and so on. And then we go from the data to the simulation models here. Once we have the models, we finish step 1. For step 2, it's very focused on reservoir simulation. Here we're going to select the model based on the best representation we need for the field. but also observing the computational time. Of course, it's much better to have a billion cells and a lot of things, but sometimes even there is no sense in having a billion cells because there are so much uncertainties that it's not very good to build simulation models that take 2 weeks to run if the uncertainties are so high. So of course, it will depend on how much reliability you have in this measurement of the data and so on. So it takes time for you to, if you are using reservoir simulation for the first time, to understand and to select the best model, what we call fit for purpose model there. But as after you run several projects, we start understanding that this is we have to find the best relationship between the quality of the results and the computational time. Okay, and here we have several examples that we can do to improve computational time. Of course, we're gonna talk about this in the course. We are gonna have to choose the best numerical model, and this numerical model here is an example. There are numerical models that run in 6-7 minutes. There are other numerical models that run in 25-30 minutes, which is just an example. So in this example, we are showing that we have of course, a representation of the same, more or less the same response with 3, 4, 5 times more computational time. So we have to be very careful when we select the numerical model we are inputting the reservoir simulation. Of course, we can use also parallel computing. Here's a representation of the simulation time for this same example here, showing that if you use, for example, 8, 9, 10 processors, we are simulating in less than 5 minutes, this specific model. If you use one processor, we are simulating 20 minutes. So it's much faster if you can use these processors. But of course, if we break the problem in several parts, sometimes it's not good to have 20 or 30 processors. We have too many parts here that we keep increasing the simulation time. So there is a best relationship between the number of processors you use and the simulation time. So we're going to talk a little bit about that in the course as well. Okay? So we have to observe this cost-benefit ratio between grids, size of grid, fluid treatment. For example, if we are using a composition model, we have to select the number of components we want to represent. And this number of components, if you use too much, the simulation time is also very high and so on. So at the end, we have to do a lot of simplifications in the models. We are going to see in the course what's the impact of these simplifications. But the most important thing here is that we have to select fidelity of the model we're going to use. Normally, we call this fidelity a medium fidelity model, and we also can have models that are more accurate than that and less accurate than that in order to take other decisions and so on. But normally, we have to select this, what we call these medium fidelity models, okay? And there are other things that we can use here. Probably Avance will talk about that, about proxy models, emulators, how much you can rely on these models, what is the relationship between the results about these models, and so on. We are going to see that also in the classes. Okay. So the green parts, I think I talk about everything here. Okay, everything is here. Anything, if you have questions, just let me know. Just almost 1 hour and just finishing the steps here. In this step, the red steps, the most important thing is to select models that honors the best. So first we go into this step 3, which is a model calibration. We can see here in the right some examples that for example, sometimes we have spurious data. Remember that we have measurements, and these measurements sometimes can be wrong. So be careful when you have real data that we have data that makes no sense. They are spurious data. We have to be careful with this data. Sometimes we have models and data that are incompatible. And this is one example of one of the projects we have of Shell. The models all have, for example, here a representation of production, the pressure of the well that's increasing. and the data that we have is decreasing. So either the data is wrong or the models are wrong. So we have to check and see the concepts of the model, if they are okay, and so on. There is no sense in starting a history matching procedure or data simulation procedure when the data is like this. The behavior of the models are completely different from the behavior of the data. Okay, we have to first to check what's happening. That's why we have this step 3 here. We try to check the productivity of the wells, the quality of the data, the type of analysis we are going to do, analyze the production, the pressure, and the average pressure of the reservoir, and so on. So after everything is compatible, it's possible, and it's okay, then we go into what we call really data simulation, and that we go. So in order to do that, first we need to generate the models. We use this method here, but you're going to face in the oil and the industry several other methods, but this is the one we are going to use in the course, where we mix here all together the geostatistic realization and uncertainties in all other parameters like reservoir structure, economic parameters, relative permeability, and so on. We mix all together in this method here that combines images of realizations of geostatistical with other parameters using the statistical technique to combine. So that's why it has this name here. Once we have this combination, we can generate several models, for example, that will represent these curves here. Each curve here is a representation of a possible scenario in the reservoir. That's why I'm saying that I have all these possibilities. So for example, 100 possibilities here, but these are not compatible with this. When these are compatible with data, then we can go to step 5. Then step 5, Celio will talk about this in one of the classes. But the most important thing here is that we have to define the process. I will not give details about this. It's just here just a representation of a data simulation process of a reduction of uncertainty. So we have to define our objectives here and our process. This is the most important part. And the process here is defined not only by the objectives, but also for the parameters that I'm going to use, the uncertainties I'm going to include in the process, and so on. Once we go here, we go to the numerical model to see if it's okay, which is what we did in step 3. Then we go into this reduction of uncertainties. We use the dynamic data to reduce our uncertainties about the future. How we're going to do that? There are several ways to do it. We're going to talk about this, but a simple model would be a filter, for example. We have generate 1,000 models, and then we select the models that are compatible with data. For example, then we have 50 models or 100 models that are compatible. Then we use these 100 models to go into the blue part. Okay, but of course the filters sometimes don't work. We need to work on that, and Sally will talk about which techniques we can use to improve this process. Sometimes we need even to go back to the characterization, what I call in the other slide the big loop. We can go back, rethink about the characterization of the reservoir if the data simulation is not working. But the most important thing is that we keep doing this until we have good models. Once we have good models, we filter the best models, considering the number of models that I want to have in the applications, then I go. Okay. Okay, here is an example where we have a water production, water rate of a well, for example, injector 19 here in this example. Here is before the data simulation, and here is after data simulation. So once we have problems in measurements and other things, we have a tolerance here. These black dots here are the history data. Here's the tolerance, meaning that inside this tolerance range, I accept the results as we have here. So this is before the data simulation, and here is after data simulation. So once we have these models that are compatible with the data, then we can rely on the future for this well. As we do for this well, we have to do for all the wells and all seismic 4D and so on, as we're gonna see in the classes, okay? Here's an example of history matching or data simulation of the for seismic 4D. So here we have a signal from seismic 4D showing that in the blue part here, for example, we have expecting at least possible gas scanning going back to solution. Here we can check that we have some pressure difference and so on. In this example, we have the simulators. Here we have the variation in pressure. Here have the variation in saturation. So we have to combine the numerical simulation results with the expected results we want to have. So once we do is a normal data simulation, as we do for wells, we can do the same thing for maps or for seismic 4D. Okay, Alessandra will talk about that as well. And here's just an indicator. I'll jump this because we are running out of time. The most important thing here is that once we select this tolerance range, which is this red dot here, red part here, all our objective functions have to be inside this tolerance range. That's why, for example, there are points here that are models that are not selected in our filters. For example, this point here is inside the tolerance range, but this model has a good result for production 1, for example, but maybe is not good for production 2, or is not good for production 10, or injector 5, and so on. So once all the models that have good results for all the indicators, all the wells and seismic 4D, then they are selected to represent your future. Okay. Why we are doing this is a multi-objective function that we have to use in data simulation, because, for example, if you select a model that is good for everything but not for producer 10, for example, then when we are going to rely on the production forecast of production 10, the production 10 will not be okay. So that's why it's important to history matching all the data in our data simulation process. Okay, but don't bother again if you don't understand some of the details that I'm talking about, because this is just a general view of everything. We are going to talk very carefully about this process in one of the classes. Okay, once the models are consistent with data, we can have a more reliable production forecast and more reliable decisions. We are using, here's just talking about the methods we are using. We are using a lot this method here that Celio is going to talk about, using a commercial software that we have from Petrobras. And we have other methods here that Celio is going to talk about as well. Okay. Okay, once we go to the blue part, I'm almost finishing here. If you remember, we divide this blue part in several steps. The first one is to select the best production strategy for our base case. We're going to talk about how we select this base case and how we optimize the production. Though, of course, we're going to detail this procedure in a while in some of the classes. We divide our parameters in 3 groups here, as I talked previously. Group 1, which are the project and design variables. Group 2, which are the operational control variables. And Group 3, which are the revitalization variables. So we have to optimize these 3. If the problem is simple, we can try to optimize the 3 at the same time. If the problem is very complex, we can separate these, optimize G1, then G2, then G3. Some of the problems we don't have to optimize G1 because the production strategy is already implemented. We have to optimize just G2. Sometimes we don't have extra spots in the platform for infills and these things, so it's just G2 and so on. So we have several types of problems. That's why we divide these in categories, and we're going to talk about the optimization of each one of these groups in particular. Okay. So once we go, this is a normal optimization procedure. In this case, just an example where we optimize the net present value here. And we optimize this value, in this case, using CMOS. We have other methods from CMG. And we select the production strategy, which the best result here, the best NPV. We can select one strategy or more than one. In this case, we select one. We look into all the indicators, NPV, oil production, how is going to be the operation, and so on. And once we go into this, we have to optimize, as I said, group 1, group 2, and group 3. Of course, we're going to talk more about life cycle optimization. So we divide this in group 2 life cycle, which is the L here. We have the group 2 short term as well. We are not going to talk too much about that. But remember that short term is the correction I'm going to do in the operation of the field and the control of the valves and the wells, if they are necessary in the short term. Okay. And the revitalization variables as well. So we're going to optimize this, find the best production strategy. Then we're going to go into the risk curve, which is, you're going to see details about this as well. But once we have, for example, 100 scenarios, combining all the properties here, for example, different PTs, different productivities, activities, different economic models, compressibilities, permeabilities, and so on. We combine everything and realizations, then numerical, just statistical realizations here. Once we combine all these in our method, we have what we call a risk curve. Here I'm showing example as the risk curve. The risk curve we're going to see a lot in the course as well. It's a risk that goes from 0 to 100% here, given all the possibilities the scenarios will generate. In this case, we can produce 35 million cubic meters of oil here, or 75, showing that we have a big difference between the most pessimistic case and the most optimistic case. And we can have this risk curve from any of the indicators: water production, net present value, gas production, and so on. So we can have these curves here. Once we build these curves, as I said, if I have too many scenarios and I want to improve the quality of the decision and the forecast, and I will do, in our group, we do that using this, what we call representative models. We are going to dedicate a few hours of the class also to explain why it's important to have these representative models. But for instance, here in green, you have all the possibilities. Each point here is the possible representation of the reservoir. So we can see that, for example, this dot here has this, with the same strategy, of course, the strategy that we select for the step 6. And we have a realization that's have this NPV here, and we have another realization that has a very much higher NPV here. Has this low NP, oil production, and this high NP. So we have all these possibilities here. It's very hard to analyze 100, 200 scenarios and optimize all this. So in order to do that, we select some representative scenarios here. And these representative scenarios that we call representative models have to, we have proved in some papers, you can read if you have interest in that. It's very important for us to represent not only the output variables, which is production and economic indicators and so on, risk curve. You can see here that the models selected in red are a good representation of the risk curve. We have pessimistic models, optimistic models, intermediate models, and so on. But they also try to preserve the input variables here. For example, if you have 100 models, and this is the PDF, the probability density function of one of the properties, I try to select models that preserve this same representation for the representative models. For example, if you have 3 possible relative permeabilities, and the relative permeability has, this relative permeability has, for example, 60% of probability to occur, this is 50, this is 40. When I select this model, I try to keep the same behavior for the representative models. So we have a special method to do that, which is our IAM finder. It's an automatic procedure that can find models that represent all the input and output variables at the same time. And once we do that, we go into this step 9, which is the step 6 as many times. I optimize production for all the representative models. Here's another example as well for using results from Unity 1, which is one of the examples we are going to use in the course. And here's the best strategy for each of the models. So if I select the best strategy for model 1, I have this NPV, for example. But if the model 1 is not the one that's most reliable, it's more close to the reality, maybe I can have, instead of 2 billion here, I can have 600 million in representative model 7, for example. Or if I rely in model 2, I can try to optimize the strategy in model 2, which is very good for that model, but sometimes it's not very good for other models here, and so on. So we can construct all this matrix here, showing that what's the result from this strategy for this model, and then I select the strategy that has the best average solution here. Just one example, right? Considering that this strategy and these models and the probability of these models to occur, then I have this best solution here. Of course, if the model that is more close to reality is model 7, I still will have a result that is not very good. That's why I still need to do some additional improvements in this model. So here is okay because everything is possible. Maybe here I will have a negative NPV, and I'm operating a small company, and I don't want to have this risk to have a negative NPV if this model 7 is the most model more close to reality, for example. Then I can do some things to improve this strategy. That's what we call, we can add additional information to see which model is more close to reality. We can add flexibility. We can have several things that we can do that we are going to talk in the course, and using these reservoir simulation models in order to improve our decision. Okay, and if we do this, for example, each of the models has a risk curve. We can select the best strategy with the best risk curve here. As you can see here, for example, if you select strategy 3, we're going to have this performance here, even with negative results possibilities here. If you select strategy 9, we're going to have much better results here in the optimistic part and not too much risk. So strategy 9 is, of course, is much better than strategy 3 and so on. So we're going to show you how to compare these curves, how go and so on. Okay, and then go to this information, flexibility, robustness, and so on. That I'm running out of time here because it was 1 hour seminar. So we are going to talk in detail about that. Susan, I'm going to talk about that. And the most important thing that here is that after we finish, it's very important for us to integrate with production facilities to check if this strategy that I select is compatible with the facilities I have, or if I need any change in production facilities, or if I have any change in the production strategy because the facilities will not be enough to produce in the way I was planning for the reservoir and so on. Okay, and then we get the final strategy and the final plan. Okay, let me jump these slides. I think this will be here just for you to. I put this slide here just for you to have in our presentation. Then in the course we can talk more about that. And I have final remarks here, but I think I talk about everything. Most important thing here that we are gonna in the course learn how to of course, build the simulation models in the green parts, do that data simulation in the red parts, optimize production in the blue part. We're gonna see classes about these topics. Then we're gonna show in some examples, and we're gonna see that if we don't do all this work, normally we have what we call suboptimal decisions. That we need to work a lot in these models, in these concepts, in order to have good decisions for the reservoir. And we're going to learn how to do this not only in the classes, but also in some of the projects. But after I finish this talk here, I'm going to explain how will be the projects. Okay. So I think that's the most important thing, and that's it. Sorry, this is. I hope it was not too fast, but you have any questions, you can make it now. Or if one of the I don't know if you want to make any comments. No comments, no questions. Are you there?
So I would like to, yeah, I'm here. Thank you very
Yes.
much for the wonderful lectures. I'm David. I'm a geoscientist, actually. So I was lost in some part of the class, but I wanted to ask a
Mm-hmm.
question. So while we take a project, let's say for instance, we're working for a client and we're taking a project from, we've done the reservoir characterization, we've defined the geologic framework. So I would like to know, what software can we use to do all the model construction and all those sorts? Are we using any programming language or something like that?
Yeah, I'm going to talk about all these details after this talk because the talk was for everybody, so I invited other people as well. But after we're going to make a break of 5, 10 minutes here. Then I'm going to talk about this. I'm going to talk about what we're going to see in every class, what software we are recommending. Of course, if you know another one and have access to others, you can use other. But we are going to use for the simulation the TMG software, which is the mainly IMAX, which is a black oil simulator. I'm going to talk about that as well. You can use Petrel for geologic parts, for example. We are going to talk about all these details about the class after the break, how will be the classes, how will be organized, and you are going to have also a project. Each one of you will have to do a project, and we divide this project in three main categories. The red or two main categories. Our application is more related to data simulation or to production strategy. But we are going to talk about in details about that after the break, okay? And as maybe others also maybe were lost a little bit in this initial seminar, but of course it's a lot of things. I talk about everything we're going to see in the course, and it's very complex. So don't bother if you don't understand. If you never have seen reservoir simulation before, and you don't understand everything, you didn't understand everything I said in this first part, don't bother because now we're going to take each of these parts and we're going to talk more carefully about all these parts. Okay,
Okay, thank you very much, Professor.
you're welcome. Any other questions?
Hello, teacher.
Hello.
Uh, if
Yeah.
you use emulators, proxy models, all these steps will be similar?
And normally, the emulators are used, emulator proxies, or even low fidelity models will be used not alone. Normally, they will have to pass through what we call multi-fidelity problems, multi-fidelity approaches, where we use simulators for some parts, but we use emulators or proxies or models that are faster in other parts. For example, let me show. Let me check here if I can go back. Just a second. I'll show the optimization parts, for example. For example, in this slide here that I'm showing, can you see this slide?
Yes.
Yes. Okay. For example, if I'm using using this process here to optimize production, for example, and let's assume that here I'm optimizing the position of the wells in the reservoir. So as you can see here, I did 3,000 simulations to get the results. Okay, I start in putting wells in some place of the reservoir, then automatically the program that uh, we are using here is most, for example, or another statistical method that keep improving the method and then find the best solution. How we can use emulators, for example, low fidelity models, for example. We see that in this part here, we are doing a lot of simulation, 1,000 simulations, just to improve the results a little bit. Then maybe if we can use, for example, do 100 simulations here, then generate an emulator, which is a very approximate solution for the simulator. Sometimes you can do, instead of doing 2,000 simulations here, we can do 100 simulation. We can generate an emulator, which is not really a simulation model, but is something that is very approximate solution for the simulation model, or even you can use a low fidelity model. Then we can do 2000 evaluation of the emulator, which is instead of hours, we will run in seconds. We can get to results close to this one. Then we can go back to the simulators. So we can use emulators, we can use those fidelity models in order to speed up the process, not to, of course, not to take the final decisions here. When you go to the final decision, then we go back to the best simulation model we have, okay? But we can use these models that are not so precise in order to avoid doing 300, 3,000 simulation in order to get the solutions. That we are going to talk a little bit about this, because all the process for data simulation, for optimization, and so on, normally will take a lot of simulation models to run. So instead of doing this, we can use what we call these multi-fidelity models. We can use a good fidelity model to generate emulators, then use emulators to optimize production, then go back to the simulation and so on. So this is the most appropriate solution. Emulators alone are very difficult to use because they are not so precise, but they can be combined and accelerate the process.
Okay, thank you.
You're welcome. Any other question? Okay, so now is, let's check here, 10:15. We can have a 5 minutes break. Then when we come back, I'm gonna talk about how the class will be organized, how will be the seminars we're gonna have in the class, and I'm gonna talk a little bit about the project we're gonna have to do and so on. Okay, so just 5 minutes. So 10:20, I'll be back here. Okay. Pessoal, tudo bem? Estão de volta, hein? Estão me ouvindo?
Sim.
Sim. Beleza. Pessoal, eu acabei esquecendo de perguntar para vocês, não sei se todos já voltaram aí, mas eu perguntei do inglês, mas eu perguntei se alguém teria dificuldade de ouvir em inglês, né? Então, se alguém tiver, me avisa aí, pode mandar pelo chat, alguma coisa assim. Tá ok se eu fizer em inglês para todo mundo? Beleza. Beleza, então, a princípio, eu vou fazendo em inglês, mas, logicamente, se tiver alguma dificuldade de um ou outro lado aí, vocês vão me avisando, tá bom? Então, okay, I was talking in Portuguese because I was asking people that if you checked if anyone would have any difficulties to speak in English, but if not, I will try to do in English. Of course, it's not so easy for me also to do it in English, much more natural to do in Portuguese, but I will try to do my best. And if you don't understand anything, please let me know, okay? Okay. Now I'll talk about how the course will be organized. So can you see my screen? I forgot to stop the presentation. I stopped the presentation. I forgot to stop the presentation before. Now I'm gonna record again in order to make separate recordings. So the first record will be about the talk, and now the second record will be about the real class. Okay. So